Yeah, so we are on point number 8 of analyze phase, and we can see that till date we have identified what are the important uh, causes which are causing variation, and by now we assume that we've already identified few theories, or you can say few propositions which are causing variation. So we would like to investigate it further. We would like to establish whether it is actually what we perceive from the data that we have collected, or is it something else. So in the analyze phase, the very first thing is creation of a hypothesis, which is basically a theory. For example, in our day-to-day life, we hypothesize that on an average we consume this much of fuel. So you can say my average fuel consumption per month is um, 10 liters, 100 liters, something like that. So how do I validate that claim? I can do so. That's what I was saying in the hypothesis testing. Uh, you have to create a theory which you would like to test. So hypothesis testing starts with the creation of a hypothesis which we want to prove, or which we want to test. Generally, we don't want to prove anything. It's not like we are biased towards proving anything. It is something like we perceive some phenomena, we perceive some theory, and we want to establish whether it is true or not. There is no biasness in this. So we start with the creating an alternate hypothesis. That's the first thing that we create, and that's what we say it is an alternate hypothesis. For example, I want to I've collected data for a month, and I found out that my average fuel consumption per day is, let's say, uh, 5 liters. So now I would like to state that in a alternate hypothesis. I would say is mu is not equal to 5, or there are three different types of the ways in which we can create an alternate hypothesis. Let's say I can say it's not equal to 5, it's greater than 5, or it's lesser than 5. And the opposite of that is generally null hypothesis. So we have to, hypothesis has to be created in a pair, alternate hypothesis and null hypothesis. Most of the times, null hypothesis represents that there is no association. I'll come to the association later anyway, but right now we can simply put it through. So there are a few steps in hypothesis testing. First, we have to state the hypothesis. We start with the alternate hypothesis, then we write the null hypothesis, and it's mostly in numeric numbers. It's quantitative. Then we have to secondly we have to suggest level of significance. Level of significance is the maximum probability that a true null hypothesis may get rejected. So it falls in the I'll talk about that later, but alpha we generally represent it by alpha. That's why alpha is written, and it indicates that what is the maximum probability that the statement that I'm writing in the null hypothesis will get rejected. The third step is determine acceptance and rejection region. So I'll explain that what is the acceptance and rejection region. It's basically pertaining to the null hypothesis, acceptance of null hypothesis or rejection of null hypothesis, depending on the statistic sample statistic that we have calculated. So we calculate the test statistic, that is if you are having more than 30 samples and standard deviation is known a priori. So we assume the test statistic with respect to the mean, testing the mean, is normally distributed. The sampling distribution is normal. If you have exactly 30 numbers, and standard deviation is known, then we take it as a normal distribution, and standard deviation is unknown, then we take it as a t distribution. If the numbers are lesser than 30 and the standard deviation is known, we still go for the normal distribution, and if the standard deviation is unknown, we go for the t distribution. So if the test statistic value falls within the acceptance region, we accept the null hypothesis. Now let me take an example. So that's what I was talking about. We consider a case where the variance is already known of the population. If the population variance is already known, then we consider the sampling distribution to be a normal distribution, and the three different types of hypothesis which you could be handling would be like mu is not equal to certain value, mu is greater than certain value, mu is lesser than certain value. That certain value we say is a hypothesized mean, right? So here your hypothesized mean, let's say if it is 5 kilometer, 5 liter per day, 5 gallons per day for your vehicle. So for the first type of hypothesis, we may state it like this: first we create a alternate hypothesis that your mean average fuel consumption per day is not equal to 5 liter, and the opposite of that would be equal to 5 liter. Similarly, for the alternate hypothesis, for the second one, you say mu is greater than 5, and the opposite of that would be less than equal to 5, and then we calculate the test statistic since the variance is already known, and we are taking the sampling distribution to be a normal distribution. We calculate the standard normal variate z with the given formula for the sampling distribution, and in case the variance is unknown, then we use this particular formula where it's a two-tailed test if it is not equal to, it's a one-tailed test if it is lesser than or greater than. So that is visible over here. We'll talk about this statistic a bit late, like when we take a problem, we'll look into the table and try to find out. Uh, these are the other types of variants of hypothesis testing when the variance is known, and then we can use this particular formula where we are trying to compare two different populations. Whether there's a difference between the two populations or not, that basically would mean that they are the same. Means the samples which I have drawn for this hypothesis, they are coming from the same population. So we calculate the z value over here given this formula, and then we can look into the normal distribution table and find out the difference and test our hypothesis. Similarly, if variance is unknown, and then we have to use a t distribution. I hope you understand this. These are certain formulas which we'll be using later on. And similarly, it can be done for proportion as well. For n binomial experiments where the precondition is that n into p, where p is the probability of success, is greater than equal to 5. Okay. And then further we have, if we are trying to compare two different proportions. And similarly, if we are testing hypothesis for variance, that is, if I am drawing a sample from a population and I would like to claim whether the variation in this sample is same as that in the population, which basically means that whether this sample represents the population or not, at that time I would like to do this chi-square test. And if I have to compare variances of two different populations and we would like to find out whether there's a difference in these two populations or not, that time I would like to use F-test. So consider this example. Air screw escape systems are powered by solid propellant. The burning rate of this propellant is an important product characteristic. Specification require that the mean burning rate must be 50 centimeters per second. We know the standard deviation of burning rate is sigma equal to 2 centimeters per second. The experimenter decides to specify a type 1 error probability or a significance level of 0.05, and he selects a random sample of n equal to 25 and obtains a sample average burning rate of 51.3 centimeters per second. What conclusions should be drawn? Now let's try to formulate a hypothesis first from this one. So basically, the population parameter under consideration over here is mean burning rate. So the mean burning rate ideally should be 50 centimeters per second. While when we have taken a sample, it's coming out to be 51.3 centimeters per second. So when we are formulating the hypothesis, we should know what is the hypothesized mean. Here the hypothesized mean is 50. So what would be the alternate hypothesis? See, what is critical to this problem statement is that it should be exactly equal to 50, not more or not less. While it's coming out to be 51.3, so we'll test it whether it is too much away from this value of 50 with the given variation, or is it close enough so that we can consider it to be 50. So the alternate hypothesis is mean burning rate not equal to 50, and the null hypothesis would be mean burning rate is equal to 50. What are the other things which are given over here? LOS, level of significance, is given as 5% alpha. It is also known as a type 1 error. We'll see why it is called type 1 and there's another type of error which is type 2 error. We'll see that in later lectures. So it takes a random sample of 25. So very first thing, we formulated the hypothesis. H1 we represent alternate by H1 and null hypothesis by H0. Okay. And now the next thing is that we have to calculate the test statistic. So X bar is given as 51.3 and mu is given as 50 and sigma is given as we can see it's given as 2 and the sample is of 25. Now since how do we decide whether we have to do a Z test or a T test? It's clearly, we know, the statement says we know that the standard deviation of burning rate is 2 centimeters per second. So it's not based on sample. It's nowhere written that it is based on sample. It is historically known. That's what it means over here. So 2 centimeters per second. And then we find out the value of Z. From the normal distribution table, we can know that corresponding to alpha equal to 5, that's a two-tailed test. So that means I have to look for left and right as well. So the critical region is on the left side as well as on the right side. Critical region represents that whether if my test statistic falls in the critical region, it basically means that my actual mean is very much different from the hypothesized mean with a given variation. So I cannot accept the null hypothesis. Hence, I have sufficient evidence to accept the alternate hypothesis. I hope you understand that. So the boundaries of the critical region to the left is 1.96 and to the right to the left is minus 1.96 and to the right is 1.96. Now that 5% we had to split it into two parts. 5%, that is 0.025 left and 0.025 right. So the calculated value is coming out to be 3.25, which is very much in the critical region to the right side of the normal distribution. So we can conclude that the variation is so high, and the mean and corresponding to that mean value of the sample, it deviates so much away from the mean that I cannot accept my mean to be 50. Hence, I have sufficient evidence to accept the alternate hypothesis. That's what the conclusion is. So you never say accept or reject null hypothesis. We always say we have sufficient evidence to accept null hypothesis, or we do not have sufficient evidence to accept uh, accept the null hypothesis, or you can say uh, we accept alternate hypothesis, the given evidence that we have. So there are ways of saying it. You never say I accept or reject null hypothesis. Why? Because it is still based on sampling. It is quite possible that uh, I may draw a sample which may not convey the same conclusion which I've got right now, but the chances are pretty less. Oh, in that case, because if I'm taking alpha as 5%, it would mean that if I do this hypothesis 100 times, let's say for 100 times, I draw different samples 100 times. Out of those 100 samples, 95 samples are going to give me the same conclusion. It basically means that. So, in fact, that's what's written over here. We conclude that the mean burning rate differs from 50 centimeters per second based on sample of 25 measurements. In fact, there is strong evidence that the mean burning rate exceeds 50 centimeters per second. Now, you may do the same hypothesis testing for a different set, like if we put greater than or less than. If you put greater than, then your critical region would be totally on the right side. If you put less than, your critical region will be on the left side. So how do I identify the critical region is that your critical region, how do I know whether my critical region is to the left or to the right when the alternate hypothesis is not equal to type? If it is of greater than, your critical region is on the right side. If it is less than, your critical region is on the left side. So testing the population of mean when the population standard deviation is known. One more example that what we are going to do. Manager of a department store is thinking about establishing a new billing system for the store's credit customer. After a thorough financial analysis, he determines that the new system will be cost effective only if the mean monthly account is more than 170. A random sample of 400 monthly account is drawn for which the sample mean is 178. The manager knows that the accounts are approximately normally distributed standard deviation 65. Can the manager conclude from this available information that the system will be cost effective? Now, in this particular example, just like the previous one, population standard deviation is known a priori, that is 65 rupees. And the thing is, what is my hypothesized mean? So let's look at the two values, 170 and 178. It's clearly written that 178 is the mean, is the sample mean. The other value is 170, which is what we can say could be hypothesized that if my cost is coming out to be lesser than 170, I would say that it is cost effective. If it is greater than 170, then we would say it is not cost effective, right? So again, alternate hypothesis would be, let's say it's coming out to be 178. So let's say mu is greater than 178. And 100 for mu equal to 170, it will like we can say the null hypothesis would be mu is equal to 170. So how do we do that? You can read that later. So we come to this set over here. Now at times I've deliberately put equal to sign in the null hypothesis, while in the sets which I've shown earlier it was greater than. In some books you would find this is the norm, that null hypothesis is always equal, while in the alternate hypothesis you can have not equal to, greater than, or less than, but you can never have equal to in the alternate hypothesis. That's a norm. Now it's your choice. You want to put a greater than, less than in your null hypothesis, you can put it. It's not wrong. So for this particular case, I may say that uh, alternate hypothesis is greater than 170, while the null hypothesis is less than equal to 170. And we want to know whether the mean account of all the customers is greater than 170, or you can say average. Yeah. So the test statistic, again, what we are going to use is a Z test, but here in this case it's going to be a one-tailed test, unlike the previous one. There we had not equal to in the alternate hypothesis, and that was a two-tailed test. But now this is going to be a one-tailed test. So here we calculate the test statistic. It's coming out to be 2.46, and corresponding to alpha equal to 5%. The Z value is 1.645. Now your Z calculated is 2.46. It is greater than your Z. We say it's tabulated. It's 1.645. So it lies in the critical region, which basically indicates that your alternate hypothesis comes out to be true. You have sufficient evidence to accept the alternate hypothesis, and we can conclude that um, we reject the null hypothesis in favor of alternate hypothesis. And the conclusion is that the system is not cost effective because it is greater than 170. So there's another term called p-value. So for the same example, if I have to find out the p-value, what I'm going to do is for the z calculated, for the z calculated value, I find out the area. If it's a greater than type of hypothesis, an alternate hypothesis, then I find out the area to the right of the z calculated value. For example, in this situation, your z calculated value uh, corresponding to x bar greater than equal to 178 is this region, red region, which you see over here. So this is to the right of. Had it been a less than, then I would have this red region would have been on the left side of the z calculated value. While if it is a greater than, the red region would be on the right side of the z calculated value. So z calculated value was 2.46. So whatever area is on the right side of it, it's coming out to be 0.0069. Now your alpha is 0.05, which basically means that this value is lesser than 0.05. That means your critical region is going to start well before this region, red region start. Means it's closer to the mean as compared to this region. Which basically indicates that your calculated value falls in the critical region and not before the critical region. Right? So this is one way of concluding. Now, why do we have a p-value? That's not only z-test or t-test. There are many other different types of tests. Now, p-value is a standard which has been created. Like you can, rather than calculating every different value z calculated and then going to the table and find out, most of the statistical softwares, or all the statistical softwares, they use this p-value. It gives you a direct indication. If your p-value is greater than 0.05, that is your alpha. If p is greater than alpha, which basically indicates that your null hypothesis gets accepted. Right? It will lie in that region of acceptance. If your p-value is lesser than alpha, it indicates that your z calculated value falls in the critical region, and hence accept the alternate hypothesis, or you have sufficient evidence to accept the alternate hypothesis. Now you can see that in this figure, particular figure over here. So with x bar equal to 178, you would have a different distribution. Yeah, so I can move ahead. It's just more and more explanation of this. You can see over here in this figure, the p-value, if it is lesser than 0.05, that means it has not crossed 0.05 yet. If it crosses the 0.05, that basically means it comes in the acceptance region. So this complete region is the acceptance region, while anything to the right of this critical value of 2 points something was there. To the right of it is in the rejection region, and to the left of it is all acceptance region for alternate hypothesis of greater than type. So if your alpha here exceeds 0.05, then this red region would cross this line and go into the acceptance region. That means your Z calculated value is in the acceptance zone of the null hypothesis. So that's what the meaning of p-value is. So why this hypothesis testing? I'm coming back to the same thing again. Why hypothesis testing is important in Six Sigma analyze stage? See, we have calculated, we've taken down so much data. We have collected data from here, there, different places, but we don't know whether this is good or not. Like whether this mean which I've calculated is an indicative statistic or not. So for that purpose, we have to do the hypothesis testing. It also happens in the medicinal field, where a new drug is devised, a new vaccine is devised, and then you would want to know what are the effects of this vaccine, whether this medicine is working or not. For that, again, you have to do this hypothesis testing. So it is a very important tool when you're dealing with the statistical data. How do I consider the descriptive statistics which are indicated over here by my sample? Can I generalize these findings? So if I have to generalize, I have to go through this hypothesis testing. So now we can do a left tail test also. So the statement is somewhat like this. Chief Financial Officer in FedEx believes that including a stamped self-addressed envelope in the monthly income sent to customer will decrease the amount of time it takes for customer to pay their monthly bills. So currently customers return their payments in 24 days on average, and the standard deviation of 6 days. So population standard deviation is given as 6, and hypothesized mean is 24 days over here. We take a random sample of 222 customers, and then they want to know at alpha equal to 10%. So they want to know whether it will be profitable or not. So it will be profitable only if mu is less than 22. So that's what my alternate hypothesis would be, and your null hypothesis, of course, is 22. Then you create a left tail test somewhat like this. So in this, you can see that minus 0.91 is the Z calculated value, and to the left of it is, why it is, because it is Z is less than. So to the left of it is minus the, for corresponding to alpha equal to 10% to the left. That basically means it's coming out to be minus 1.28. So minus 0.91 lies in the acceptance region. I would advise you to find out the p-value for the same and see what is your conclusion. Two-tailed test we have already done, so this is some example for you to do it later. I'll skip through these slides. You can do that. Yeah, good. So it's a diagrammatic representation. You can see the green region over here is indicating the critical region again, where the null hypothesis gets rejected. Yeah. So that's it for today's lecture, and we will see other types of tests in the next lecture.